Hello, thanks for coming to our first edition of JOTB meetup. I want to thank all of you for coming, and especially DIKW Intelligence for this event. It's the first time we do this in a meetup format, so hopefully it will go well. Before introducing the two speakers we have for today, I would like to explain, give some news about Jay on the Beach and what we are doing. And the first news is about a new event that we have launched, that it will take place in just 3 months. We have barely started to organize it, so it's going to be a really good event, a great event. And it's going to be focusing in most of the profiles that we don't do at Jay on the Beach. So it's more about user interfaces, front-end developers, UX designers, product designers, and things like that. It's also going to be an international conference, but it's going to be a bit smaller than what Jay on the Beach is. It will take place here in Malaga on the 15th and 16th of, you cannot see it, but yeah, 15th, 16th, yeah, that's it, December. If you are interested in user interfaces, this is going to be your event. Second thing is about Jay on the Beach. Next year, it's going to be in May, on the 10th and 12th of May. And the idea for next year on the beach is that we are going to grow in terms of people, attendees, and speakers. Last year we did a data science track. Next year we plan to increase that track, so it will be also. Traditionally, Jay on the Beach has been bringing developers and DevOps together around big data. Next year, we are also bringing data scientists together with the other two profiles. Last thing, let's meet the speakers. We have Hugo Koopmans, sorry for my Dutch, Chief Data Scientist at DIKW Intelligence, and also he's CTO at Clues Sensing.
Sensing Clues.
Sensing Clues, sorry. Yeah. And we have also Miguel Gabarrón, who will speak later. He's our local speaker, but also working in an international company from the UK. And we just brought them here to give us some idea of practical use cases that you can do with data science applied to the natural environment. So with Hugo's talk, we will see how we can use artificial intelligence to how to localize wild animals and to find insights to what these animals are doing, and also just to try to protect them, of course. And then with the talk from Miguel, we will see how they are using big data and big data technology for geolocalization and to optimize crops and help farmers to get the best of their results. Okay, so please, a big applause to Hugo, and let's change the.
That's already good. An applause before I ever said something, but that's good. Let's change first.
Yeah.
See if the stream still works. Ja, deze doet het. Dan moet deze het. Yes, yes, yes. Excellent. Let's see if this works. Is that okay? Is the stream still there? In the back also, yeah? You can hear me, Remy? Excellent. Okay, thank you for coming. Traveling all this way to Malaga to just hear me talk. That's very nice for your you guys there, and maybe you guys are a little bit closer to home. So thank you for coming. Yeah, today we want to talk about what happens when data science meets nature. Yeah, let's just kick it off. I brought three main topics: the vision, the challenge, and what DIKW actually does for sensing clues wildlife intelligence. So yeah, let's go ahead. Our vision is, when Tim Berners-Lee invented the World Wide Web back in 1991 or something, HTML, etc., he had vision, and that vision was to connect anything with anything, machines, man, etc. We didn't understand what he meant, so he reinvented the web in 2000, and he called it the semantic web. And we are now 20 years later, and we still don't understand. So yeah, we have to figure out what he actually meant. Facebook moved to the graph DB in 2007. I think Google introduced a knowledge graph in 2012. And Wikipedia is a semantic graph database by design. So I think at Sensing Clues, what we started in 2015 as a very successful project from DIKW with the Dutch National Police, was a sort of a spin-off of that project. And we thought maybe it's a good idea to start with the enterprise knowledge graph right from the start. So let's see what that brought us. So the vision is actually you should move to the enterprise knowledge graph. Maybe not as soon as possible, but it's a very clever idea to do. So what is the challenge? In 2018, I was at a semantic web conference in Vienna, and I met Alain Morson from that time he was working at PwC, PricewaterhouseCoopers, and he had a great pitch, so I borrowed some of his slides. So there's actually three types of innovation in IT that you can think of. The first one is incremental. We just keep adding to our technology stack. We keep adding stuff. The second one is what we see now, cloud, movement to the cloud is actually virtualization. And the question is whether this virtualization effort actually helps reducing technical debt. So what you see is actually you hide away complexity in the cloud. You are reducing complexity, but in reality that's not necessarily true. And so the last type of innovation is actually data-centric. So I think if you really move to a data-centric IT organization, you really do something about the complexity of your IT environment, right? So that is actually the idea of putting data at the center of everything you do. So I also talked here to senior colleagues here from DIKW, and what you see is when we design data warehouses, when we design data models, in practice it turns out that we not model that many concepts actually, right? 10, 15, 50, maybe 100 concepts is a lot, individual concepts. Right? So what is actually the problem? What is the bigger problem? You could argue about that, but what artificial has and what it needs. So what it needs is actually contextualized, disambiguated, highly relevant, specific integrated data. But in practice, well, at least in my practice, I just have data sets all over the floor, and I still spend 80% of my time collecting data, munging it, etc., to make it a little bit useful, a little bit workable. What we would love to have is knowledge engineers, bold data visionaries, big D data scientists, etc., etc. But what we actually have is a growing group of tool users, right? The discussion R versus Python is still alive very much. And we don't need that. So what the problem is in innovation is not necessarily technology. We don't necessarily have a technology problem, right? We think we have a sort of a tribalism, right? A groupthink, etc. That is actually at the core of innovative inertia. So, well, the machine learning edition, I don't know if you favor yourself in any of these groups. So there's several groups of people who believe in certain technology is better than others, and they stick to that. And they are not looking away or across the chasm that actually prevents innovation. So for data integration, same thing holds. We used to put everything in relational databases because that was the only database that we had. Then we came into service buses and we thought, oh, that's a good idea to integrate systems. Now we are in this microservices idea that I think is by itself a good idea. But still, that prevents us from truly becoming data-centric. That's the idea. So, so the challenge that we have to really work on integrated data-centric way is that we have to be aware of where our innovation comes from, and we have to see that purely from an innovation perspective, which has nothing specifically to do with data, these tribals are actually causing a big problem for true innovation. So enough about the big idea. Let's just move to some more detail. So Google thinks it's smart, the knowledge graph. Successful big US companies think it's smart, putting a graph at the core of your data. Tim Berners-Lee thought it was smart, so he reinvented the web several times, but that was still 20 years ago. But I truly see some traction now for this way of thinking. So the question then is, how does it work? How does a knowledge graph work? So I can talk hours about that, but I think I only have 10 minutes left now, or I don't know. Where is our time boxer? I don't know. So from strings to things. So we have the string Leonardo da Vinci, and we'd like to recognize a true entity, something real. And then we have connections between Leonardo da Vinci and other recognized entities. So we can actually build a data model like this. Dots and edges between the dots, and these dots and these edges actually mean something, truly mean something. That's the idea of a knowledge graph. So for instance here, Bob is interested in the Mona Lisa. Bob is a person, and I think this is really cool. That person is metadata, and Bob is an item, is an instance. And so the metadata and the data are actually described in the same language. I think that's really cool, but maybe I'm the only one, I don't know. So there is already a lot of linked open data out there. That is RDF described, etc. So that is, you could say that the World Wide Web is truly our database. And that's the vision that Tim Berners-Lee actually has. So now back one step smaller back to our company. DIKW has some semantic use cases. We started in 2013 or something, hacking LinkedIn. Thought that was a cool idea back then. And then we did a very cool accident about road accidents at our traffic department in the Netherlands. And in 2015, I stumbled into Jan Kees. He worked for the Dutch police, and we actually put together sensing clues. So now let's see what sensing clues is and how we help sensing clues with this knowledge graph. What can we do with this knowledge graph? So the idea is we turn wild spaces into safe havens. The mission is we believe that the huge potential and the using of the power of data as a key enabler to boost nature conservation. And Sensing Clues provides professionals with the affordable and the best of industry data-driven methods. The same methods as we use for our company, we also use that in this setting. So at this point, we are live in 18 projects around the world. And the idea actually is that we help these guys here, the protectors, to grab the poachers at work. And not only the poachers that actually do the dirty work, but also try to find the network, the bigger network behind these criminals, right? That's the idea. But it's not only about poaching. There's a lot going on that is illegal or that is actually harming nature, harming wildlife coexistence. So there's a lot of work to be done. So how Sensing Clues actually works, it partners with champions in the field, in specialists in the field, and we are one of them. And we deliver data science technology and data science expertise, database expertise. And that is actually how DIKW plays a role, but there's a lot more technology providers that actually play a role. So what do? We have some methods that help people on the field to better understand what is actually going on in their nature reserve. So for instance, I don't have a good Spanish example, but in Holland, so we work for a park that is the size of a Dutch province of Utrecht, and there is only 50 people there. And that's, so 50 people are actually driving, walking around in the size of a Dutch province. So they can't see everything, right? So what we actually need is something efficient to collect data. So the first thing when we started, we built the data collector, which is an Android phone app. And because we are rooted in the Dutch police, Jan Kees is from the Dutch police, and for him, real time or near real time is the standard. If it's not near real time, it's not actionable, so it's useless. That's annoying that you have somebody like that in the board, but actually get stuff delivered, so that's cool. So the big idea is helping rangers. So we started out with thinking about very clever sensors, and we tried to get that working, but it's very hard to do. Building IoT stuff, connecting it to a satellite, making sure the sun shines, while having some battery, it's really hard to do. So then we moved to giving people a phone and making it deadly simple to just record everything you do, right? And from there, we can do really cool data science. So one of the things, if it's the dry season, you can drive by car in the east of Africa. If it's the wet season, you cannot. So this is a live roadmap that estimates the distances, the time that it takes to actually travel from A to B. Sometimes roads are gone, sometimes roads change, sometimes roads are not even there. And by just looking at what is happening on the ground, how are people moving, we actually have a live roadmap that changes with the season. Wow, I think that's quite cool. We also do risk maps. So here you see charcoaling risk map, and what that means is that we collect data for people burning wood into charcoal, and charcoal is fuel to cook. It's illegal. And then the idea is that because we keep track of where people are and what they record, and we also keep track of when they not record anything, the difference between that gives you an indication of risk potential, right? So that's one of the things that is currently live. So this is Moses, our analyst in Tsavo. This is Tsavo East in Kenya, and one of the things that we do is we provide him with an application like you see here, which is in the headquarters, and it answers the 6-7 golden questions. It's the what, the how, the where, the when, the why, and that type of question is the questions that we actually try to solve. We do some basic reporting still at this point, but it is sufficient. And what is a real challenge is that we have to keep it simple, really, really simple, because not everybody there actually can read, for instance. So we have to use very simple techniques. So here you have an example of collecting data, observations. This is density of where have I looked. If I look here in this place a lot, I also collect a lot of data. That's obvious, right? Because I am there a lot. And if I subtract these, then I can see here, okay, I've been there, I've collected there, but probably I should go there, because the yellow here, the heat map says, there is a lot of potential here to actually find observations like this, right? So that is actually how we help efficient patrolling, for instance, right? We use satellite imagery to actually combine and extrapolate this data with this kind of satellite imagery and create a map like this. So what we actually do is actually moving. So because we have a graph database at the bottom of this technology, we think we are very flexible in moving and adding new APIs, new data sources, etc., etc. So what you see the last couple of years is a lot of talk about data fabric, and I think a semantic layer on top of all your verticals, all your data verticals, is a very good idea. It's a very good idea to do that. So technology-wise, we say, okay, we have raw input, and we have what we call an ontology that actually describes all the concepts that we know of. And we put this raw document into an envelope design pattern. That is how the database provider that we use, how they actually use that. And we build search indexes on top of that. And those are multimodal, so those are triple searches, full text searches, and regular database searches, right? So combining these different indexes, it turns out to be very flexible and very powerful. So we use Pool Party to actually do the data modeling. It's a semantic data modeling tool. And we recently actually released a new version of the app, which now makes it possible for the whole chain to be driven from this ontology. So as soon as we change the data model, the app changes, the behavior of the app changes, the data is stored in the proper way, and the reports also automatically adapt to the new definitions in this data model. And we think that's very flexible and very cool. So a small example, an idea. So this is actually what is recorded. People tag documents. So they actually have a human activity and they tag it. This ends up like XML or JSON LD in our database. So this is a document where there's all kinds of tags all over the place, and these tags actually create a graph, right? So that is, in a nutshell, I know this is very, very fast, but in a nutshell how it works. So what do we plan to do? Sans Inclus has recently received a big funding from the European Union. And the aim is, so we are now at this level, I would say, and we are now looking at digital twins. Can we actually create in this knowledge graph a semantic AI, graph AI, that behaves as a digital representation of what is actually happening on the floor, on the ground? So we have 4 years to figure out if that works. And well, maybe in 4 years we're here together, and I'll show you if we got it right. Very challenging idea around digital twins. So not sure if there's a lot of work. There's a lot of work. Okay. Well, I only talked about our WITS toolbox. So we do also cool data image recognition. It's Koopmans. We were actually runner-up last year in the Kaggle competition. We were only beaten by the University of Brazil in Manaus. And we also have a sound sensor that is like an artificial intelligent ear that doesn't, or that is actually edge AI, that classifies sounds as it hears it and only sends the classes to the cloud and not the whole not the whole recording, right? So yeah, we do very cool stuff, and of course that's proudly powered by DIKW, and yeah, we are very happy with that. So why DIKW? I think we have a proven track record in semantic technology, and we focus on innovation. We have a solid framework for services in data science, BI, and data warehousing. And we have some cool partners, won some awards. And this year we are here from 2007, so 15 years, celebrating here in Malaga. So yeah, that we do something right if we are here for 15 years. So I think that's great. Thank you guys for listening to my talk. And that's about it. Thank you. This for me.
We'll have all the questions after the second talk. Another thing is that I forgot to mention is that right after all the Q&As before the drinks, we'll have all the questions after the second talk. So we probably have a number. Another thing is that I forgot to mention is that right after all the Q&As before the drinks, we will do some raffles. So you probably have a number. My colleagues gave you, but only we'll do some raffles with them. We have some food, JOTB, welcome bags, and some t-shirts and some extra prize. But all these we have very few numbers, so I hope you have a big feed to feed on that.
No, to them.
Toch maar een andere naam. In het Engels is het toch moeilijk.
Ja.
Intermediate. Ja.
Perfecto. Hola. Hello.
Aquí, la pantalla que tú tienes.
Vale.
Hola. Hello.
Perdona, tienes la otra pantalla. Tienes esto seleccionado. Claro, te lo voy a poner bien. Es que se ve aquí la pantalla que tú tienes. ver si ahora funciona. Si no, pues nada, como así. Vale, te pongo... Ah, claro, es que estás compartiendo tu obra diferente. Bueno, pues entonces...
Es igual una que otra, ¿eh?
Vale, venga, es igual. Ponlo como tú quieras.
Hi. My name is Miguel Gabarrón. First of all, thank you for coming and thank you for inviting me to talk here. I'm going to talk about intersecting big geospatial data for economic insight. Hi. So, my name is Miguel Gabarrón. No. Thank you for coming and thank you for inviting me to talk here, but not there. I'm going to talk about intersecting the geospatial data for economic insight.
Ah.
So,
Maybe you can try
no.
the slideshow. Doesn't work?
No.
Should be
Both
done.
here, but not there.
So it's working here, but but you have the USB connected to the...
Now, yeah,
Now it's working or not?
yeah. So, I'm going to talk about. I will talk about data in agriculture, yield, planting, and soil. Section order. I prefer to tell a story rather than giving block of informations. Then I will talk about different approaches we try to solve the problem, and finally about the solution that I think we are on the right track to achieve. So, first of all, how's data in agriculture? We have a hierarchy. We start with the grower. Every grower has farms, and every farm has fields. And at this level, we start having geometries. Every field has operations, and operations are planting, yield, scouting for pests, fertilizer, crop protection, whatever. And these operations are assigned to the field, and they have metadata, crop, field, season, data specific to the operation, that for yield is yield rate, for example, and also geometries. So it looks like that. For a field F, crop corn, season 2021, we have a planting, for example, operation with variety A in one section, variety B in the other section, or a yield operation with rate X or rate Y. So our challenge is intersect yield layers to planting layers, intersect yield layers to soil layers too, and that's a very different problem, as you will see. Has to be accurate enough, and also has to be fast enough. So, how's the process of joining two layers? We join on the metadata, we join on field, season, and crop. We do a cross join, and you know a cross join is a Cartesian join, so it's problematic. Then we intersect geometries, and this is the expensive step. This is done in 3 sub-steps. So we first check if the geometries intersect. Then we have a yield layer, we have a planting layer or a soil layer. We intersect it, we get the 4 polygons, and we calculate the statistics. In tables, it looks very similar. We have the yield table, the planting table or the soil table. We do a Cartesian join, and then we intersect all the polygons that have the same field, season, and crop. But layers are much more complicated than that. And I'm going to tell you now how a yield layer or a planting layer is generated. This is a field. Imagine you get there with your combine. There were plenty of icons of combines on the internet, but all of them copyrighted, so I created my own. You go there, you have your root, so you start collecting data. And for each point, because this is point data, you have the position, your timestamp, your yield in kilograms or whatever unit, the moisture, speed, is either up or down, a lot of sensor calibration. We have a lot of data for that single point. Then you start traveling the field, you realize you are there alone, not a lot of traffic, so you speed up, and the points start to be more scattered. And then you go to the headlands, and then you have to turn that big combine slowly, so your points are very close together, and then you find a light post that you need to go around it. So this is a mess, and you end up with a lot of points, but points are not really very useful. You know that at that point you collected 3 kilograms of corns, but 3 kilograms in 1 square meter, in 3, in 5. So you need to convert those points to polygons. And that is a very important department in the company, and it's a very complex algorithm. First, they need to convert all the proprietary data formats from all the companies to a standard format, and then they need to apply complex algorithms to go from points to polygons. They use the combine speed, the header position, the flow speed, because the yield is measured on the top of the combine, so it needs to travel from the header to the top, and that takes time, so you need to make a kind of adjustment for that. You use the GPS, the timestamp, a lot of data, and you get from this is a real yield point data map, to this. Polygons that are covered by these two cells together with some more. And this is when you generate the cell and explode, this is by this function. For cell 1, because it's completely contained in the polygon, you have that is core, and you don't need a geometry. You will know why. And for cell 2, it's not contained in a polygon, so it's not core, and you generate the intersection with polygon 1 and with polygon 2. And this is really cool because now any other polygon within this cell, you know that the intersection of this with the polygon 1 is going to be this. You don't even have to see if they intersect. You don't have to do anything. You don't waste time doing that. And coming back to this case, this is really useful in these big to small intersections, because all these cells are core for these soil units. So you know that all the polygons in these cells, you don't even have to try to intersect them. You know that the intersection with the soil unit is going to be the same polygon. How did it go? For yield to planting, it was worse than our manual index. And we think it's because we generated a lot of small polygons from planting and yield that we need to intersect them. So that took a lot of time. You can see the indexing is not very different, but the intersection is. So from 70%, we save 58%. But now, for yield, using resolution 12, we further improve the times from 35% of savings to 73%. So now, combining the two approaches, we are 70% or more better than we were in our original purely geometric intersection. So next steps. Wait for S2. We want to try S2 instead of H3. Hope they release mosaic explode without clipping cells, so we can use that same function for the manual indexing. We want they are going also to incorporate row-based error handling, and this is very useful because you have to change from different geometric formats within operations, and we work with 15 digits of precision, which is a lot. When converting, you can have very small precision errors that breaks geometries. When a geometry is broken, the whole job fails. So we want that when a geometry is broken, only that row fails, as it happens when you work in your local, but not in distributed. And of course, we have to go to production. That is the difficult step. Before finishing, just thank the team that has been working in this project. I have forgotten a past member of the team that left the company for different reasons, but I'm sure they will forgive me. And that's all.
Okay, Hugo, you want to? Any questions? So with me, Hugo and Miguel. So. Okay, Hugo, you want to? Any questions? To either Hugo or to Miguel?
How they move under certain circumstances? Is my understanding correct that you want to create like a version?
Yeah, that's okay.
To
Okay.
see how they
Oh yeah, that was a question for me, Martijn. Thank you. Can you repeat the question again?
You mentioned you will write on digital twins
Yes.
or so I was wondering if you could try to create
question for me.
Okay,
thank you.
Yeah.
Yeah, so creating digital twins is an idea of, well, you build a model and you know the model is wrong. All models are wrong, some are useful. So what you try to do is you try to also learn from the simulations. So you draw simulations from them and then you actually see whether the simulations are also measured in the field or are popping up there. So yes, so we want to learn by creating the model, learn how the behavior really is. Yeah.
And then you actually see whether the simulations.
Yeah, eventually, of course, if the model actually advances and gets more complete, you hope to catch more of the real behavior of animals, animal interaction. Yeah, so that's the idea of a digital twin. Yeah.
Yeah.
We also use that in the harbor, for instance, in the Rotterdam harbor, and we also use digital twins to really understand how people are actually using the environment.
Behavior of animals, animal interaction. Yeah, so that's
Any other questions?
We also use that in the harbor,
No one's
for instance, in the Rotterdam harbor.
on your
also
side.
use digital twins to really understand
No, that's
how
fine.
people are actually using the environment.
Okay.
Any other questions?
Thank you very much. Another applause, please. Thank you. So now, can you bring the Megan? Where are you?
Okay.
Now it's time for the raffle. Thank you very much. Another applause, please. So we've got some. So now, can you bring the Megan? Where are you?
Hello everyone. How are we doing today?
So now it's time for the raffle.
Talks, yes. Okay.
We do for the
Alright, so now it's raffle time. Thanks again to the speakers.
So we've got some
So
gifts.
we're going to be raffling off 5 of these. How are we doing today? 4 of these talks, yes. It's Friday. It's Friday. Alright, so now it's raffle time. Thanks again to the speakers. So we're going to be raffling off. Stick around after that because also in the back. 5 of these IoT, 4 of these IoT sets. Oh yes, it's fully. And also 6 of the Jam on the Beach 20. So we're going to read them off all at once, and then stick around after that because also in the back we'll have some more. Alright, we're good. So, yes, or not number 1. So the first one. 18. So, let's begin. So we're going to read them off all at once, and then
Goodies,
to the back of good. Okay. Alright, back. Number 1. Okay, number 9. Not number 1. So the first one. 9. 18. Alright. 18. 17. 9. Good? Okay. To the back. Thank you, sir. Okay, number 9. No, 20. That's a 9. That's 9. All right. 17. Cool. Nice.
Hey.
Ladies power.
2. No, 20. I gotcha. I'm keeping you on your toes.
But that's Friday.
Okay, 21. Nice. 16. I don't like that number.
How many agencies does that still have?
Yes, please. One more.
Cool. Next one.
You didn't like the one.
I don't like that number. Number 6. All right. Number 5.
Number 5 over here.
One more.
Last one. Lucky
Excellent.
number 10. Yes.
10.
Perfect. All right, so that's it, folks. You can head to the back if you want a prize, and then also if you didn't win a prize, there's more merch for you.
Yeah.
For the medals.